This is going to be a talk on outlier detection and time series signal. I'm going to introduce Bugra Akyildiz. He works as a machine learning / NLP engineer at CB Insights, where he applies machine learning algorithms to NLP problems. He receives his BS from Kent University and MS from the New York University, focusing on signal processing and machine learning. So let's welcome him.
Thank you for everyone. So today I'll be talking about outlier detection in time series signals. This is from XKCD, as you may guess. So we have data, but data has problems. We have missing observations, noise, outliers. Today I'm going to talk about mainly for outliers, but I'll also introduce a FFT-based approach to remove the noise from the time series signals as well. So outliers, why are there is because there are logistical problems either in transmission or transcription. There are experimental errors, erroneous procedures, measurement errors, component failures, and so on. But to begin with, what is it, right? What is an outlier? There are people who define outliers in various ways, but I'll stick with this definition, not because it captures the best in terms of what an outlier is, but I guess it captures the common sense of the people when they think about outlier. Today I'll talk about 3 different methods. One of them is medium filtering approach, one of them is FFT based, and the other one is Monte Carlo Markov chain model. So to begin with medium filter, yesterday Ryan talked about how naive Bayes is a punching bag of the classifiers. I guess today the medium filter is the punching bag of the methods. It is quite simple. We are just sliding a window size W and then replace the original value with the data point. As you may guess, the median is not linear. Doesn't smooth the signal, unlike an averaging window, and it is robust to outliers. So this is a toy example. We have an original signal X, and we slide over window size W3, and then replace the value with the median value. In order to handle the first and last values, we extend leftmost and rightmost values to compute boundaries. So the original signal is the left, the signal with outliers is the right. What we want to try to do is to be able to capture or at least detect the outliers and remove it from the signal. So this is quite simple approach. We first get the difference as abstract the median of the signal. This difference is called median absolute deviation. And then we get the median of that median absolute deviation, and then look at the median difference. If it is smaller than some threshold, this threshold is arbitrary, and it depends on how much you want to capture or how much you want to preserve the variance of the signal. And then we put a mask based on that threshold and then return the signal. So this is the first one is the medium filter signal. The second one is the original signal. You could just ignore the boundaries because I didn't handle for this specific case, but it introduces also some problems around here and here because the signal varies a lot. But overall, if we compare with the original signal, I think it is quite successful. At least we reduced the variance of the outliers quite a lot. So the baby elephants don't know how to use their trunks to drink water. They get miserable whenever they want to drink water. We know a powerful tool, FFT, to deal with time series signal. FFT is useful for both noise removal and also outlier detection. Noise in the sense, noise so differs from outliers in the sense that it doesn't necessarily distant from the main signal. It may travel on top of the signal. and also not necessarily random. It may be modeled as a Gaussian noise, or some background process may generate those noise, and also may have dependency to its original signal. The first one, so the FFT is actually a misnomer. When people say FFT, they actually mean discrete Fourier transform. FFT is just a particular implementation of how to compute DFT. It is from Cooley and Taki from 60s, but the algorithm itself is so successful, and nobody actually talks about DFT, even if when they say FFT, they actually mean DFT. The first equation is how to go from time series signal to frequency domain. And the second one is the how to go from frequency domain and time domain. The term e to the minus j 2 pi k over n may seem a little bit dangerous, but I will simplify that in a bit. So this is actually the original algorithm, FFT block. This simplifies the computation of FFT, computation of DFT from O(n) squared to n O(n) log n. It is a recursive method. If you want to take 18-point FFT, you could kind of divide into two 8-point FFT, and then you could recursively also divide the 8-point FFTs into two 4-point FFTs, and so on. The Euler's formula is handy in order to compute or at least to reason about how to compute FFT. The term e to the minus j2 pi k over n gets simplified by using Euler's formula with a bunch of cosine and sinusoid of x. And so what is Fourier? So we have a signal, like smooth signal. It varies, but not too much. When we compute the DFT, we get some frequency component, which actually corresponds to the frequency of the cosine. In this case, cosine 1x corresponds to 1, cosine 3x corresponds to 3, and so on. What's good about FFT is when you have an arbitrary signal, which really doesn't look like a sinusoid or cosine, you could kind of fit different frequency of cosine and sines to get, or at least to approximate the signal with different coefficients of the cosine and sinusoids. So this is, sorry. Oh, come on. Oh. So in here we are trying to approximate the square wave with a bunch of sinusoids. And after we accumulate kind of a lot of sinusoids, we could be quite successful. And sorry about that. Anyway. So when we want to remove noise removal, the left one is the original signal, and the right one is the signal with noise. This noise is just a Gaussian noise on top of original signal, and it has also some DC component. So it is not just high frequency signal, but also low frequency. The original signal is 5 Hertz, and we want to be able to remove the noise from the signal totally. So when we take the DFT of the signal, the frequency response looks like this. The y-axis is log scale, so the difference between those two guys and the rest of is actually quite different. These two guys is actually 5 Hertz, which is the original signal, and the remaining frequency components are just noise, as you might guess. So in frequency domain, we could just detect those frequencies and then remove the remaining frequency components and to get the original signal. So the first one is the original signal. The second one is the noisy. And when we apply the FFT, this is also called bandwidth filtering, bandpass filtering, then we get a original signal, which has a frequency component at 5 Hertz. So how do we use this one to remove outliers? Noise is easy because we know exactly what we are targeting for, at least in frequency sense. So we could just slide a window like we do in the medium filtering case, and then get the frequency response of the signal in that window, and then look at some arbitrary fmax. This fmax corresponds to also the variance or the jump that we want to capture or want to preserve in the signal. And then if that signal is, if that window of signals frequency component is larger than fmax, then for each observation we just look at it and then remove it and then take FFT, and then unless the signal's frequency is smaller than fmax, we just remove those. This is the Python implementation of the algorithm. In here we have also the frequency amplitude in order to capture how much the original component that we want to get, but the implementations are relatively straightforward. And the second part is just sliding window case. We are just looking at a window and then get the outlier positions and then return them. So in the first outlier signals, this is quite successful, and unlike medium filtering, we didn't disturb the signal any case, but we are able to capture all of the outliers. So the third method that I'll be spending some time, outlier detection via Monte Carlo Markov chain. So today, Joshua Bloom talked a little bit about how they are using MCMC to estimate some of the distances of the planets. This could be somehow related. We are also trying to estimate parameters in the signal. So Monte Carlo Markov chain is actually a combination of Monte Carlo sampling and Markov chain. Monte Carlo itself is useful for estimate parameters of a distribution. This could be any characteristics of a distribution. Markov chain is a stochastic process to get or to sample different states from a stationary distribution. MCMC kind of combines both of the goodness of both Monte Carlo and Markov chain. We design a Markov chain in such a way that we actually get the target distribution's characteristics by sampling the different states. So an easy metropolis Hastings sampler in order to get the posterior distribution could be designed in this way. So we have a time indexed signal, x1, x2, xt. We just initialize x1 to a random number. We have a proposal distribution to sample the candidate value. And assuming the transition matrix is symmetric, this is our decision criterion. If we want to get that observation or not. That is basically about it. So how do we implement in Python? Is like this. So we start with number of iterations. Also, we put some burn-in. Since we are initializing to some random number, the first samplings wouldn't be very useful in order to estimate characteristics of the distribution. So we just don't want to include in our resulting posterior distribution, and we these posterior distributions and proposal distributions are arbitrary. Whatever you want to capture in your model, you could design in that way, and then the acceptance criterion as I showed, it just looks for the minimum value of the with one and the possible candidates proposal distribution value, and then we flip a coin, and then if the acceptance criterion is above that, we include the observation. Otherwise, we don't, and we do this iteration until the number of iterations gets. But the problem is this implementation is very simple. Generally, doesn't really work well because it doesn't have convergence properties. It doesn't provide anything very useful out of than the sampler itself. Generally, PyMC is the, as Joshua Bloom also already mentioned, PyMC is the maybe de facto library that has been used for I would even say for general Bayesian modeling. So it is actually to start. It is a little bit hard. There is a book from Kim Davis-Pillen, I guess probabilistic Bayesian programming for hackers. That could be a good start if you are not familiar with library. But it looks like quite NumPy computation, except the decorators. So this there are 3 different decorators. One of them is potential, the stochastic and deterministic. So in this implementation, there is no potential, but maybe I could tell a little bit about deterministic and stochastic. Deterministic means we have parent variables, and we are trying to get the child variable in the sense that we want to sample from parent variables. Deterministic means if those parent variables are deterministic, then the child variable is also deterministic. PyMC.stochastic, even the parent variables are deterministic. The child variable is not necessarily deterministic, but could be a stochastic variable. So in this example, I didn't show what signal we are dealing with. So in this case, we want to capture these outliers. But this signal looks like a linear signal. In this case, we want to also do a linear regression on top of this signal by removing those outliers. In this case, we have just slope and intercept model. And then we have an outlier model, which is a likelihood of the outlier we want to capture. This is a Gaussian. This is based on a Gaussian outlier. Basically, what we are trying to do is we want to get rid of the observations that have high spread, high variance, and then preserve the ones that are somehow aligned with the slope and intercept, and then run our MCMC on top of these models. So these are the posterior distributions. In the y-axis, the first graph shows the slope. Oh, and this signal is 2x plus 10. The slope is gets maximized around 2. The intercept gets maximized around 10. Unlike the FFT and median filtering approaches, we could also reason about the outlier information, which is, I think, very useful. We could get the outlier probability of the signal, spread of the outliers. I mean, we could get these characteristics of the outlier from after removing from the original signal as well by using FFT and median filtering. But this is like built-in in Monte Carlo. So this could be another advantage of using it. And in this case, it does really well. So this is box plot of outlier and original signal. As you may guess, the outlier signal has higher variance than the original signal. The mean values are also different, but that doesn't really tell much about the outliers, as we are more interested in the variance of the observations rather than the means. So why this is important? Generally, statisticians give a high importance to the confidence intervals. And if you want to estimate a parameter and it is a huge confidence interval for like 95%, then generally that parameter estimation may not be good in general. So removing outliers and then doing parameter estimation would be useful for those cases. And as you may expect, since we are able to capture 2x plus 10 signal, we could also detect our outliers by MCMC. So how are we doing on the? So yep, we captured our outliers. So to tell a little bit about which, so I don't want to say both three methods are working and you should be happy. Generally, this signal, the real data sets are quite different, quite hard. In here, we could play the God, I guess, since we know the parameters, what we want to estimate in the first place. But Bayesian approach has, I think, a lot of advantages over the FFT and medium filtering approach. So if the, generally, if priors are not known, but we have a lot of knowledge around models, how noise is generated, or how at least we could reason about what does outliers look like, and if our models capture that type of information quite well, I think even if the priors are not known, that doesn't really matter at the end of the day. The second, if the priors are known, generally you can't really use the priors in the frequentist approaches, but you could just easily incorporate into the Bayesian models as prior information. Also, it is probabilistic. You could kind of reason about probabilities of the so it doesn't produce just one number. You could say, it could be 2 with this probability. It could be 10. The intercept could be 10 with this probability. I think it is also another useful thing. Also, if the model that you are trying to capture are more complex, and you may have some knowledge around what type of process could produce outputs, you could kind of build stacked approaches, different models, more complex models in Bayesian setting, whereas you generally need to cascade different systems in the frequentist methods. So also it has a couple of disadvantages. So in FFT, medium filtering, we didn't do really anything beforehand. We just look at the method and then run on the signal. But in Bayesian setting, we need to do a lot of careful planning, what type of priors we are using, what type of models we are trying to capture. So these, all of the inference schema should be designed and should be known. Generally, frequentist, I guess this is one of the biggest disadvantages of Bayesian modeling in general. Both computation and also algorithm-wise, frequentist approaches are just very simple and also runs faster than, for example, Monte Carlo Markov chain. And hopefully, we learn a little bit. Yeah, this is also. So there are a lot of discussions around when to remove outliers and how to deal with it. This is, I guess, a good anecdote that if you need to decide also after you captured the outliers if it is actually an outlier or it could be a valuable data point in general. Also, it may provide a much different information than what your general signal looks like. Hopefully, we learned a little bit about how to use our trunks, even if not to drink water. We could just do that. And the credits, one of the visualization actually didn't really work well. Maybe I could go over that one a bit. I think that explains quite well. But so this is our signal. This is a bunch of cosine signals. This is, if you remember, e to the minus j 2 pi k over n term. So what we are trying to do is just get the correlation with the original signal and to get the Fourier coefficients. So at the end of the day, we have a bunch of Fourier coefficients which corresponds to a discrete Fourier transform. And this is original signal looks like. In our case, the frequency component is a bunch of noise components and also our original signal. Yeah. And yep. So the source of the presentation is also in my GitHub repo. The visualizations are taken from the one ukas vb.tumblr, and the first image is from XKCD. And I guess, yeah, that concludes my presentation. Thanks. I guess we have some time.
So in your first example, how do you pick the threshold, if any?
This is in general, so in FFT also, there are two parameters that needs to be somehow defined. I think that is quite application dependent because at the end of the day, it really depends on how much you want to capture, right? Like if you want to really be flexible and then get the quite outliers, like quite distant ones, then you could put high threshold. But if you want to be conservative and if you have a predefined range for your signal, then you could maybe lower that threshold and then do it that way. Generally, like a global threshold may not work in general. The sliding window approach, I guess, remedies that disadvantage of that problem because if you have a time varying signal, even if it's smooth, when you put a global threshold, at some point the signal kind of goes over that threshold, and when you just remove it, you may also lose the original signal. But for the local threshold, I guess it depends on how much you want to really preserve, how much you want to capture.
So you mentioned using cascading FFT to detect outliers for more complex signals. How do you compare that with the Bayesian approach? How the results compare?
So we have seasonal data. I think periodic signals in general, FFT is way to go because it is easy. It is kind of, you could easily get the frequency components quite well. Maybe you could kind of get quite easily the frequency components of the signal. And if you have a really periodic signals, then the frequency components would be quite high, and it would be rather easy to just get rid of whatever below threshold. But I think if you have the computation power, and also if you know the models that you want to capture, in this case linear, and if you have a similar to sinusoids. And if your model kind of could imitate that process in some way, then I think in general I prefer MCMC because it is probabilistic. In FFT, you don't get really a lot at the end of the day. In MCMC, you kind of get like also the characteristics of the distribution, the outlier information. But I think if you have a like very regular periodic signal, I think you may want to go with FFT. Yeah.
So you partially replied already, but for non-periodic signals, FFT is ruled out, right? If you don't have a like a quite periodic signal, but if the signal varies slowly, like it is not jumpy signal, right? So generally the natural signals are like this, low pass, like low frequency signals. So what you could do is just get a portion of the signal, like a low frequency range, and then remove all other parts. This is actually called low pass filtering, what averaging windows are actually doing. But if you have both like a slow frequency component in the signal and also high frequency, so some may imagine that we have a signal over some range which varies slowly, and then it gets quickly, right? Then it may not be very easy, but in MCMC also you need to design the model in that way. I look at the signal. If the signal's range is somehow limited or regular, if I want to capture the low frequency, I would go with FFT. But if I could design the model to capture the signal itself, I would go with MCMC, I guess.
I'll do one. So can you talk a little bit about the tools that are currently available in SciPy or scikit-learn that are, you showed a lot of code, how you implement these things from scratch. Are there just any canned libraries, signal processing? Which ones are the best in Python that you found?
In signal processing, I generally use SciPy and NumPy. NumPy has FFT built in, and also a bunch of signal processing tools that are available. I generally depend on those. Scikit-learn doesn't really have anything useful for time series signals, although the other stuff they get really well in time series signals. Even like a hidden Markov model doesn't exist in scikit-learn. So I guess NumPy and SciPy are like very good. Also, the neuroimaging people produce like have a lot of available toolbox. Sadly, I'm not using any of those. But if you are doing something like more complex wavelets or something that is more involved in time series signals, you may want to look at those. Scikit-learn has an implementation for outlier detection, but it is not time series signals specific. It looks at like 2-dimension or high-dimensional space, and then it uses an SMV one-class based approach to detect those outliers. You may want to also consider if your kind of signal is not in time series, but like image or text. One question from there. Yes.
You mentioned Monte Carlo Markov chain. How do you deal with the error? Just through repetition, or do you do something special?
So in general, PyMC provides a lot of convergence, but that is like one of the biggest problems that I found in experiments. whether I should increase the number of iterations or should I do something in the model itself. So I generally look at the trace. PyMC provides a trace and error functions. If those functions seem not to decrease over time, in the sense that number of iterations, and the end result doesn't really look anything useful, then I assume something problematic in my models. And if the errors somehow gets gets decreased over time, but not necessarily fast enough, then I guess you need to look at a little bit about PyMC internals. With general, I find myself, why does this decreases fast enough, or why does this decreases very slowly? I found generally myself in those situations. PyMC generally is a high-level library, but has a lot of internal like flags, parameters, optional parameters that you could tune in. Generally, MCMC somehow depends on the parameterization a lot. So you may want to tweak those if the error is somehow medium level. Yeah, you could tune the parameters basically.
All right, thanks everybody. This concludes this talk. We'll have breaks right now, and then I guess converge back here for a keynote. So thank you very much.
Thank you.